So I'm brand new over in the CS department. I've spent my dissertation and my time at IBM focused on node link visualizations predominantly. For those of you who were in my class, what are you doing here? Because you've seen this all, but thank you for coming anyway. So visualizations are often just kind of a fancy name we use to refer to plots and graphs and other pretty pictures of how to understand your complex data sets. In this case, we just have a simple scatter plot of a data set known as Anscombe's quartet. And based on the spatial position of these circles on the screen, you can see that the trends in these 4 different series of data are markedly different, right? So that's the standard scatter plot encoding. You have one axis, you have another, you align things based on those axes, and you see, well, we have this diagonal line, and an outlier, we have a vertical line, and outlier, we have a curve here, we have something kind of like a line, but the spatial position is how we're able to pick that up. The human brain, in combination with our eye, can find those patterns in a fraction of a second, as long as we as designers have done an effective job of encoding that information so it can be perceived. In a node link network visualization, where you have the nodes and the edges, that spatial position isn't generally provided by axes. It isn't generally provided by underlying data attributes. Instead, we try to come up with a somewhat arbitrary position for those nodes that best exposes that underlying topology in the network, best exposes the relationships. This is the same network on both sides, but with a better layout, you're able to see that it looks kind of like a cube here. For a larger example, let's take a look at US politics, and let's go back in time to a simpler time, a happier time, 2007. Right. Now this is the network of all 100 US senators. Right? And they have a connection between them that's weighted based on how many times they vote the same way on bills. Right? So if Chuck Hagel and Ben Cardin agree 45% of the time, then this edge would be weighted 0.45. Now here, it's a complete graph. Everybody has voted with everybody else at least once. And so the trick is to first filter down to a subset of the edges below some threshold. But we still have an unmanageable visualization. You're not able to interpret much about this until we then adjust the layout. So applying an automatic layout algorithm to find an effective positioning for these nodes, the exact same network, we're able to see these 2 distinct groups of senators that have similar voting patterns, as well as the people along the middle who bridge the divide there. This importance of spatial layout has been recognized in a bunch of perceptual psychology studies too. First, McInally in 1986 created this scale for what kinds of encodings are most effective for quantitative tasks, and position just blows everything else out of the water. This has been replicated by here in Bostock later on, although this is the chart from McInally. Again, for quantitative tasks, position, phenomenal. But even for ordinal nominal tasks, position is the most valuable thing we could use for this encoding. So back to node link visualizations, if what we care about most is seeing the structure of the network, the topology of that network, we want to use position as well as possible. And this has applications in all sorts of exciting disciplines. I'm sure you've seen talks on many of these already as part of the seminar series here. One of the first projects I did in the network visualization space was try to design tools to help novices in these very disparate fields get started doing node link visualization of their network data. And because many people, especially sociologists, have their data in Excel, or at least they did when they started this project, we built our tool inside Excel. It was called Node Excel. It's a template that drops into the standard Excel platform. You have your worksheets where you can store your nodes and your edges, and any statistics you calculate, any clusters you find. There's filtering options that you can use to reduce the amount of data you're trying to show on the screen. And of course, the node link visualization with a bunch of different layout algorithms and options for presenting the data and encoding it using color and shape and size, all of those exciting things. And that served as a wonderful platform for conducting some research on new techniques for creating these node link visualizations, which I'll be talking about in this talk today. Now, let's take a look at an example of how different layout algorithms running on different software platforms can produce very different results. So here at the top, we have 3 different networks, roughly small, medium, and large, running in using the D3 force layout. That's a JavaScript implementation of a force-structured layout algorithm attempting to find a position for these nodes. And then in the bottom, we have, again, a web-based visualization, but this time, the layout algorithm is being computed on a server, and then the results are sent to the front-end client. And on the server, we have a C++ implementation of a best-of-breed layout algorithm. Let's start a little race. Let's see how they do in terms of time and performance. All right, so we have a countdown, and they're off. Okay, wow. Things converge pretty quick. Even in these modest to large-sized networks, we're able to get pretty reasonable results very quickly. And even this one, which we had to super speed up in order to get to the layout algorithm to finally stop, finally get to a point it was happy with, the basic structure was there from the beginning. But still, it was faster to compute things on the server side, especially for these large networks. Now, they look pretty similar across the 2 layout algorithms, except in this case, there's something weird that happened here. Right, here we've got kind of a tangled ball, and here we have something that looks a lot more like a tree. Looking a little bit more closely, we can actually see that pattern being exposed. The D3 force layout makes everything this sort of amorphous blob, while the SFDP layout running in C++ actually exposes the tree-like structure of this data set. Right, so speed, while important, is much less critical than getting a layout that will be meaningful for the end user. If you look at this, you'll think everything's roughly connected if you're not paying attention to the exact connections. But how can we evaluate something like this? Right? If we try different layout algorithms for the same networks, we get very different results. There's a lot of papers about this, just how these layout algorithms compare with each other. And if you're not an expert in reading these things and understanding these things, if you're developing a tool designed for novice users, you can't just give them all these options and hope they'll get to something that will be meaningful for them. Instead, we want to quantify how effective these layouts are algorithmically. And so people have done a lot of work on understanding the perceptual psychology behind how we read these visualizations. They've done user performance studies. People have defined simple rules or heuristics based on the results of those studies. We'll have these massive tables of rules that you want to apply if you're designing one of these things by hand. But it's virtually impossible to keep all of these things in mind and optimize them manually. Plus, it's a ton of work. So Helen Purchase proposed these aesthetic criteria at the first attempt to quantify all of these different principles algorithmically. And then I extended her work and then also added local metrics for individual nodes and edges to direct people to where problems are in the visualization. And here's some examples of these metrics. So one basic principle you want to try to avoid in a node-link visualization is reducing the overlap between nodes. Here in this video, you see as we change the size of the nodes in the visualization and we start getting some overlap, the metric is calculated and the color coding shows how much overlap there is. And this is a problem in the case of labels. Like if you have a label attached to these nodes, you don't want them plotted on top of each other where you can't see those labels. But if things are seriously overplotted, even if you don't care about the labels, you're not going to be able to see how many nodes there are. Right? You can have one node here, or you can have 100 nodes here, or 1,000 nodes. If your layout algorithm places them on top of each other, and the nodes are large enough, you're not going to be able to see what's there. Another metric that I developed is for edge crossings. If you've done work with node-link visualizations, that's the primary thing people talk about trying to avoid, getting rid of those crossings as much as possible. You know, in this case, we have one edge that's totally fine. We have these two edges that are crossing this edge here, but they're not terrible because they're only crossing at one edge. This edge between node A and P is in a much worse situation. In the video here, you see the effect of this playing? Well, the video would have shown exciting color coding there. Anyway, but what people often don't think of is the angle that those edges cross each other. Perceptual studies have shown that you can actually get away with having more edge crossings as long as you make the angle that those edges cross about 70 degrees. You'd think, well, why not 90 degrees? I mean, that's as opposite as possible, right? But that perpendicular intersection actually tricks the eye into thinking something is happening there. Right? What does that mean, that exact 90-degree intersection? So instead, we try to just be a little bit off, but we don't want to be acute because your eye might accidentally track one of these other paths accidentally. So here you see an example of just some very, very acute intersections causing those types of problems that we quantify. One last metric I'll talk about is distance coherence. This tries to quantify the difference between the graph theoretic distance between two nodes, that is, how many hops you have to take along edges, versus the Euclidean distance on the screen. You just have to draw a straight line here on the screen, how far are they away from each other. Ideally, you want one hop in the graph to be about the same distance on the screen, no matter what edge you're caring about. And so this metric that we developed captures that. And so if you have these super short edges, in comparison, they're weighted, or they're colored purple. If you have super long edges, they're colored purple. Just you want a nice default there. And so here's an example of some of the metrics we've talked about, other metrics that we developed. These are both a single measure for the entire visualization, as well as measures for individual nodes and edges that we can then feed into algorithms to improve, or into color coding for humans to improve. And if you're curious, I suggest you take a look at our paper here from 2015, where all of these things have wonderful mathematical definitions, so you can actually implement them. But it's also implemented in Node Excel, the tool I mentioned a little bit earlier. Any questions? Actually, so if you guys have any questions as we go, feel free to jump in, because there's two distinct parts to this talk, and I don't want you to lose track of any questions you might have. Yeah.
Have you worked with other kind of layouts other than force-directed?
Yes,
so this
but is there anything
for laying out networks? Because they're always like, if you have a large enough network and you run it like 5 times, they always look different. So that's something. So there's a lot of subjectivity in this like force layouts, and I'm just wondering if you have if you also like looked at other approaches to attack this problem.
These force-directed layouts are tricky because they're non-deterministic, like you say. They're just heuristics saying, well, if we do it this way, we generally get good results, but they're very dependent on the initial positioning of the nodes. If you're doing a random initial positioning, like so many do, you'll get very different results, and they will sometimes converge into local minima. There isn't an awful lot we can do about that within the space of force-directed layouts, just based on how they're designed. They're trying to solve a very computationally intensive optimization problem as quickly as possible. There are other layouts, like I'm actually blanking on the name, but it's the one where you have multiple axes and you draw the connections between the nodes across the axes. There's circular layouts that you then reorder to try to reduce the number of edge crossings. I worked on these group-in-a-box layouts where you have a deterministic way of placing the clusters or groups in the network, but then within them you're using a force-directed layout or a circular layout or something. Polar layouts based on attributes. There's a ton of exciting opportunities. People like the force-directed layouts because they do best at exposing the topology, as long as you have put some effort into making sure that the result is good. Let's take a look at another data set here to motivate the next part of my talk. This is a subset of genes that a user has searched for. We have them listed up here, and then in blue are the conditions that have been extracted from medical text that are associated with those genes. So this is just a tiny subset somebody might see if they were doing a search in their organization's tool for these types of connections. Now, even in a small network like this, we'll see exciting patterns, especially once we apply color coding and size coding to show you, in this case, the strength we've identified between those connections. But it does start getting a little bit complex, and you might notice some repeating patterns in here. We've got all of these conditions up here that are only connected to one gene. Likewise, down here, right here, we have these singly connected conditions. And then in the middle, we have these groups of nodes that are connected to 2 or 3 genes in very similar patterns. And so one of the first observations is we've got these motifs, these regular repeating patterns in the network. A little bit different from how people think of motifs like with protein-protein interaction networks, but I'll get to more explicit definitions in a sec. These motifs can dominate the screen space that you have for your visualization, these giant fans on the outside, and the functional equivalent. So what can we do with that? Well, in the past, people have said, all right, let's find functionally equivalent groups using some sort of heuristic or algorithm, and let's replace them with sized metanodes. This gets us less stuff on the screen. People still know how many things are being replaced. Ideally, if we're defining functional equivalence effectively, this will be very meaningful. The problem with this approach, though, is that all of the topology, all of the relationships in that functionally equivalent group are then gone, completely opaque to the end user. And so what I did instead was say, let's take very particular motifs, like these fans that have a very high payoff, and replace them with representative glyphs of that underlying topology. Right, so not arbitrary topology, but very particular sets of topology. Likewise, those connector groups that we've seen, of nodes that only connect other groups together, let's replace them with this tapered diamond glyph. These glyphs are chosen to be somewhat unique amongst the standard palette of shapes people use in their like visualizations. And so when we take this gene condition network and simplify it down, we now have a lot less stuff on the screen, which is fantastic for a human, fantastic for a layout algorithm, fantastic for rendering in a web browser. It just becomes a little bit trickier to read because you have to know what these shapes mean and what the size of them mean. So there's a tiny bit of a learning curve there. Let's talk a little bit in particular about what these encodings entail. So if you have a lot of nodes that are being replaced from the singly connected fan into a fan glyph, you get a large arc glyph. So you have arc and area encoding there of the number of nodes. If you have very few nodes, you get a small arc glyph, and then somewhere in between, you get somewhere in between. Now, if you have a color coding attached to these nodes that's mapped from an underlying attribute on the network, so it may be just how frequently it occurs in a medical article on a blue to orange scale, we can preserve some of that information. Let's just apply a function like the average or the median or the mode, and take that function to put it on the color scale and get a color for the glyph. We lose some information there, but at least we haven't lost anything about the topology. And we can expose the attributes through interaction. For the connectors, it works much the same way. Lots of nodes are replaced with a large glyph, very few nodes with a small glyph, and so on. Color coding, again, is applied as in the case of the fans. And then here, we also have these sized meta edges that replace the underlying edges between the nodes. So if we have a strongly weighted edges on either side here, we see that in the simplified visualization. If it's unbalanced on one side or the other, we can see that imbalance in the simplified view. Again, the attribute information is aggregated, but the topology is lossless. So let's look at some of these examples here. So we have the simplified view. We can, with interaction, just mouse over one of these nodes and blow it up and see what's inside it. And now we can use a different layout algorithm that's better suited for what the specific task we care about, which is seeing the things inside that connector motif. Here, it's just a list. We can easily scan and see which of these conditions are actually relevant to the task that we're trying to accomplish, looking at this network. And here we can also see, based on the strength of the connections, all of these are highly connected to IL-10, they're all highly connected to IL-17A, and very weakly to CD86, which was also visible in the aggregate meta-edges. Blowing up this large connector on the side, we see that we've replaced a huge number of weakly connected conditions between IL-10 and IL-17A. But through this interaction, we're able to see a nice scannable view. One last motif I'll talk about is clique motifs. These are completely connected groups of nodes. Every pairwise connection exists. And these will replace with these rounded X's, again, sized and colored according to the number of nodes that are being replaced and the attributes of those nodes that we haven't encoded for. Going back to our Senate network to show how these cliques work, we start with our 65% filtered agreement network. Let's take this and apply the clique motif simplification technique. So it turns out that all of the Democrat and independent senators actually form a complete graph. It's this large blue X that represents the Democrats and independents. Down here in the bottom left, we see almost all of the Republicans, but we have this moderate Republican clique that votes more with the main Republican Party, but votes a fair bit with the Democrats and independents. And then we have Coburn, party wildcard, who's just off doing his own thing, right, at 65% agreement. Filtering a little bit farther, now we're at 70% agreement. The node length visualization looks much the same, a little more sparse, but then the simplified view starts getting kind of interesting. You see Olympia Snow here, highly connected to the Democrats and independents. We've got the main Republican Party clique. We've got Collins and Specter here that are gatekeepers. They actually were part of that original moderate clique, but now they've split away. This was many years ago, but imagine a beautiful animation that you could do with modern technologies to show them coming out. And then we have a new moderate clique, still containing John McCain. He's been in both of these times, in these filter slices now, but he has new moderate members from the Republican Party that break out. And then on the left, we've got Coburn, who we saw before, but other party wild cards and folks who vote with their heart, Bitter, Voinovich, and Hagel. At 80% agreement, the network completely bisects. There is no collaboration across party lines at that point. Simplified view, we finally see the Democrats break up from the main party into the far East Coast liberals and independents, including Bernie Sanders. We've got Nelson and the other moderate Democrats. And Nelson, at the time, the pitiable blue dog, moderate Democrat, doesn't vote at all with the East Coast liberals and independents. On the Republican side, we see substantially more splintering into smaller cliques. I ran a user study to evaluate how well this technique exposed its underlying relationships and whether there were any serious downsides with this technique. I looked at 3 data sets. One that I've shown you here, the Senate data set, and then 2 others. This wiki network is very similar to the example I showed you with the drugs and genes, the conditions in the genes. And then this is a large web crawl network. And I'd like to point out that this is one of the only studies on node link visualizations that uses networks more than 100 nodes. The examples that we tend to use tend to be pretty small, and so it was exciting to actually try this out with large, more realistic network data. So I had 36 users come in. It was a between subject study. Half of them got node link views, and half of them got simplified views with a small set of interactions that they could use to explore the data. And I asked them to perform 36 different analysis tasks, very low-level, granular things, about how they would interpret these network visualizations and learn things about them. I won't present all of the results, that's in the paper if you'd like to take a look, but I will show a couple of examples. One interesting thing is the case of labels shown next to the nodes. Right? How does a simplified view affect users' ability to find a labeled node? Right? In the case where the label is visible in the simplified view, like it's one of the nodes that haven't been simplified away, and also in the case where the label has been hidden inside one of those simplified glyphs. I imagine like one of those single nodes in one of those fans. And let's take a look at how long it takes people to find it and whether they're able to actually do it. So in the case of and these are the three different networks that we have. In the case of this network, in the unsimplified view, which is blue in this case, nobody was able to find it. In the simplified view, a handful of people were able to actually find it. Everybody was able to find it, and they were able to do it fairly quickly. Sorry, misreading my notation. In this case, it means 3 users dropped out for that time. In this case, users were able to find the labeled node much more quickly, and they were able to find it in all cases. This was the Senate data, so it's only 100 nodes. People can actually look at everything on the screen, and it's a data set that they might know about. And in the final case, many more users in the simplified view were able to find the labeled node, and they were able to find it much more quickly. Now, in the case where the label got simplified away, it turns out that if there is an impact with these size of networks, it's relatively unsignificant. We found some marginal significance in one case that users were taking a little bit longer in the simplified view, but there didn't turn out to be any other significant differences in those cases. It's possible just by running more users we'd see more differences, but the running hypothesis is that at this scale of network, trying to label everything is just going to be next to impossible to identify individual nodes with those labels unless you eliminate some of that complexity. So simplification was a natural win. Another task users might want to perform is estimating the number of nodes in the entire network. Right? And it turns out that users, in my studies anyway, vastly underestimate the number of nodes in the network. But in the case of simplified networks, they underestimated a lot less. Even in the case of the Senate data set, which you figure people would know how many senators there are. In terms of how long it took, users would actually take longer to do so, though, at least in two of the networks that we looked at. They'd spend more time trying to interpret what the glyphs meant, but then in doing so, they'd have much more accurate predictions. So those results and many more are available in the motif simplification paper, which was in the ASIM SIGCHI conference. Also, algorithms for identifying these three different kinds of motifs are presented there. There's a bunch of case studies in that paper, as well as some of our other work that you can take a look at. And it's available in Node itself if you want to try it out and play with it with your own data. One thing that I'd like to pitch to all of you is that in this coming September 25 through 27, we're going to be hosting a conference on these topics here on campus. It's the 25th International Symposium for Graph Drawing and Network Visualization. It has 2 separate tracks. So one track is applied network visualization, like what I've shown you here today. It's design techniques and applications to real-world data sets and tools and all the pretty things. And then there's the other track, which is theory behind graph drawing. So focused on planar graphs and other classes of graphs that you might care about. If you're interested in submitting papers, we've got a deadline of June 12th to submit there. But even if you're not interested in submitting, I strongly encourage you to attend or find a way to be involved. Feel free to come talk with me about if you have any clever ideas for how the Network Science Institute can be exposed better at this conference. It'll just be at the Alumni Center, which is over by Ruggles. Also, if you are looking for classes for the fall, I'm going to be teaching my special topic course on visualization for network science again. Leo and Sid are here. You can talk with them if you have any questions about it. They were my guinea pigs last year, and the course will be much improved based on their feedback and their experiences. But in this course, we're going to do a deep dive into different layout algorithms and techniques for evaluating them, as well as edge bundling algorithms and node overlap removal algorithms, and even totally different ways of visualizing networks, including matrices, as well as complicated matrix techniques like node tricks and seriation to reorder things. So this gets into a deep dive into all the algorithms that I haven't talked about today. So I strongly encourage you to to sign up if you're interested. Right now, with that, I'd like to open it up to any questions you guys might have about my work, about network visualization in general, about how you can get involved in graph drawing. Thank you for your time.
Any questions?
I just, by the way, I'm Laura Stryker, and I'm just starting to work with the new Global Resilience Institute here at Northeastern. And I think there's going to be a number of great opportunities for collaboration. But I was just wondering, you know, I hear this and it makes me think about what a valuable tool it could be for epidemiology research. And if you know of many instances where you've seen that intersection with health, and, you know, one of the things is typically public health is like, well, tell me what you're going to do with my data and then I'll give it to you. Whereas this makes an argument for give me your data and I'll tell you what's in it. But I was wondering if you had any experience with EPI.
So Alex actually has a ton of beautiful visualizations specifically focused around epidemiology. In fact, I worked on a project with one of his previous postdocs, Nick LaPera, in which we tried to look at how influenza spread across the world through a combination of node link visualization and also morphed map techniques. There's that data tends to get super complex because you have people from all over the world traveling.
Well, that's what I was going to ask. At what level is the data? I mean, could it be looked at, or have you looked at it at the local, you know, from the local to the state to the regional to the global levels?
Yeah. So in that project, we looked at the global level, just in terms of a morphed map projection. So you could see all of the regions of the world that we had subdivided, as well as in terms of this aggregate node link visualization, where you have each region of the world a separate polygon, and you'd see the connections between those regions. And then to look at individual areas within there, you could zoom in and see these roughly hexagon-shaped basins that represented the.
I'll have to look into that, yeah.
Yeah,
Because I think there's tremendous potential for it. Yeah.
It's a very nice tool, let me.
Yeah.
Good job, yeah.
So one of the most interesting things I've seen visualizations being used for recently is these hypergraphs where you're thinking about not just dyadic relationships, but you know, these 3 people are actually friends, or 4 people are in a room talking or something. Have you seen? We've just seen little bits of these things in conferences, but not developed well at that point. So have you seen that kind of thing? Where almost like you can color in sections that indicate, you know, this is actually a group, not just 4 or, you know, a set of dyads.
Just trying to see if I have I might have an example of that somewhere in the deep bowels of my slide deck. It's very similar to the problem of overlapping set visualization. And so the most common things I've seen are just any other table. The most common things are just to draw these connected edges somehow and indicate that they're connected. Right. I'm sorry, let me rephrase it. The most common thing is just to turn it into a normal graph rather than a hypergraph and just have that deal with that explosion of edges. So people will have these kinds of edge drawings. For the overlapping set, specific type visualizations, there's all these really cool things you can do, like kelp diagrams, where you have your nodes, and then if you have your hyperedge or your set, you can draw this almost organic looking this organic looking shape around the things connected to that set or that hyperedge. Is there anything in particular you've seen that?
I've seen it not kind of not overlaying another object on the network, but actually somehow indicating the hypergraph with some kind of coloration of you know, like almost like filling in the section, like that's what I remember seeing, where it's like, you know, like you fill in the sections that indicate some, just different ways to show that there's some kind of group activity rather than sets of diamonds, you know. But I'll follow up with you about that, because I've seen some kind of cool things.
This was a really, so I think in the example I'm thinking of, it is filled in. And then if there were overlapping hyperregisters and such, they'd actually have different sizes, like a topology visualization. So if you have a note here, or this set, we would then have a subsumed little shape filled in on top. And so you'd see the outer layer is like one layer in the topograph and the inner layer. Yeah, it would be interesting to talk about and see the examples here.
Any other?
So you said that you're extracting your data from Excel, for instance. Has it, can it be applied to pretty much any database? Because it's very flexible in terms of.
Yeah. So these are just general techniques I've been talking about. The Node Excel tool was designed for you to just copy and paste your data into from whatever tabular format you've been able to extract it in. But I've developed techniques that access JSON APIs or that read directly Microsoft Access database files, CSV files. It's fairly agnostic because it's not really tools I'm talking about, more just techniques that are built on a subset of those tools generally.
Is there a network visualization version of p-hacking? I mean, how do you, when you're playing around with different visualizations and make it certain features more apparent, less apparent, how does the researcher defend themselves from accusations that, oh, I just picked one of 100 visualizations that makes the result I'm interested in look the most obvious?
So finding a way to quantify the thing that you're claiming based on the visualization is probably the most effective way. You run your statistical analysis, you do whatever validation that what you found in the visualization actually matters, is actually significant, and then use the visualization to help convey that story in the final publication, rather than just presenting the visualization and saying, hey, look at what I found. But a lot of visualizations, especially link visualizations, can suffer from the things you're talking about. You can have things that look like clusters that are artifacts of the layout algorithm. Perhaps the worst case is some layout algorithms, like I know one of them that was implemented in Node Excel, do not deal with different components of the network well. And so they'll actually lay them out on the same screen space. And so you have disconnected components drawn on top of each other, and when they should be just totally away. Right? And there aren't good general techniques for quantifying those issues, except things like the metrics that I've developed. Right? If you have an implementation of those metrics and you say, all right, how well are this set of clusters that I have algorithmically identified represented in this 2D layout? Like, do these clusters overlap, or are the components overlapping? Actually just measuring that and saying whether or not there's a problem is the only real technique that I see, aside from sending it to an expert user.
Great, so Cody will be kind of hanging around for the next hour or two, so grab him if you have specific questions. And downstairs at roughly 3:15, we're going to talk, so anyone downstairs, grab him there. Thank you so much, Cody.